title of my talk is The Breakthroughs in Search for Technosignatures, and I hope by the end of my talk that will make sense. I'm going to start with this question: what is SETI? So I want to ask this question to all of you. If you can raise your hands if before today you have heard the term SETI. Oh, wow. Okay, good. So hopefully you all know then what it means. In any case, for those of you that don't know, SETI is a search for extraterrestrial intelligence. And it's a field of research which basically is between, you have here astrobiology and communication technology, and SETI lives somewhere there. Through time, there have been many different institutions where they have done SETI in one way or another. I think at this moment, the two main ones are, probably you have heard about the SETI Institute, and I'm part of this one, the Berkeley SETI Research Center in Berkeley. So I'm going to tell you more about my work from that. But I'm going to actually start my talk now with an introduction in perspective of astrobiology and how there are several ways that we want to find life outside our planet. And I think basically there are three different ways, and we have heard talks about this today. So basically we have in situ sampling, exoplanet atmospheres, and SETI. For in situ sampling, I think the cool thing about this one is that you basically doing a direct detection of life. Either you go to Mars or some of the moons of our solar system, you will be able to find some kind of life. You're looking for fossils, as we heard, maybe that's more difficult. In contrast, these other two methods are remote sensing. You're finding signatures that life, in one way or another, creates, and you can interpret those as life made by life. So the first one is when you're looking at the atmospheres of exoplanets. As we heard from Andrew earlier, we have what is called biosignatures. So you're looking at the atmospheres, and by looking at their composition, you can realize if there are some elements there that the only way that you can have them is because some biological process is creating them. In the case of SETI, we have what is called technosignatures, and I'll explain more about that later. One extra comparison that I want to make about all of this is that we might think that in general, looking for microbial life or simpler forms of life might be easier, or it's easier to create, so it might be actually easier to find. But actually, I think there is a reason why I think SETI is in equal footing with all the other options. And that's the range. So if we have in situ sampling, at least for the next couple of decades, I think that we are very much bound to a solar system, and probably even less than 10 planets or moons that we can search for life. For the case of exoplanet atmospheres, with the coming of BWST, I think we're still bound for nearby stars. And that might be, I don't know the numbers exactly, but somewhere around, say, less than 100. For the case of SETI, if we first limit ourselves to the same level of technology that we have, we could already look for millions of stars. And if we allow ourselves for advancements in technology, just extrapolating from our own technology, not going to something crazy, we could easily get this number much higher. So even though finding intelligent life somewhere else might be in a way harder, I mean, the probabilities of creating intelligent life might be much smaller than just life, just by having larger numbers that might compensate that. Something that all of them share is that we don't have any other examples of life. We don't really know how common is life elsewhere. So we can say that by the lack of constraints, it is equally likely that we live in the only biosphere in the galaxy, or there are thousands of them. The same thing you can say for civilizations. But I think, as Carl Sagan said, and this is very much at the core of any SETI experiment, is that the only significant test for the existence of extraterrestrial intelligence is an experimental one. So what we're trying to do is make an experiment and trying to figure out if there is something out there. Okay. So far I've been telling you about the search for extraterrestrial intelligence, but actually I'm going to tell you that I don't do that. Yeah. We're actually doing is the search for extraterrestrial technology. And we use technology as a proxy for intelligence. So here on our own planet, we probably have several examples of what somebody could call intelligence. But in order to communicate or in order to figure out if there is life at very large distances that is intelligent, then the only way will be, kind of an example here. We're looking for intelligence that can create very large buildings, for instance. And the type of technology that we're actually interested in is examples that we have in our own technology is communication technology. So finding a way to send a message across very large distances. So these are some examples of that. So for instance, we have very high power TV or radio stations that can basically go around our planet. They can actually, those signals can go for many light years from us. The strongest transmitter that we have in our planet is on the Arecibo planet, is called the Arecibo Planetary Radar, and it's in the Arecibo telescope that you might have known before. This is a 300-meter dish in Puerto Rico. And it's so strong that you can actually use it to map the surface of asteroids, nearby asteroids in our own solar system. It's pretty cool. We also have examples not only from radio, but also from optical, where you can have basically a laser, very powerful lasers that, in principle, if you shine it to a different star, it could outshine at those regions our own sun by thousands of times. Okay, so you can see that so far what I'm telling you is electromagnetic waves. And there are reasons why electromagnetic waves we think is the way to go, is a venue for communication. And sometimes we have questions from people saying, okay, what if they're using, I don't know, tachyons or neutrinos or gravitational waves or something else? But there are actually reasons why electromagnetic waves is a very appealing method. And I'm just going to list some of them and tell you about that. So the first one here is that they're easy to generate and to receive and very cheap to make. And that's obvious, right? So all our technology is based on this. So the Wi-Fi in this room, radio stations, and many other things are all based on this kind of technology. They travel the fast speed possible, and that's the speed of light. So we know from physics that there is nothing that can travel faster than that. So you can imagine whatever high technology that you can create, the fastest rocket out there, still it will be slower than this. Wrong way. There is also another thing about electromagnetic waves that help us on this, and that's that you can easily distinguish artificial-made signals from nature-based signals. And one example of that is Voyager. I really like this spacecraft, and thanks for telling us about it earlier. So it has been traveling for several decades now, traveling through our solar system, and it's just now outside of the solar system. And it has a transmitter of 40 watts, which is what your typical fridge light bulb has. And we're able to detect that very easily. So that's a very clear example to me that how, with a very amount of energy, you can send a message across very large distances. So this is an example of actual signal from Voyager. This is kind of the data that we look every day. So you have here frequency and time. So earlier on, from Brandon, we're looking at spectrum, radio spectrum. So in this case, what we call this is a dynamic spectrum. So every time step, you can imagine you have a spectrum and it's evolving in time. In this case, we have this very narrow band signal. And coming back to my topic here about having an artificial signal is that if you see here on the numbers, it's only 50 hertz wide here. And there is nothing in nature that can create a signal that narrow. the narrowest signals that nature can create, masers and so on, are thousands of times wider than that. So you find a signal that is this narrow coming from somewhere else, that already telling you, okay, that's something interesting. All right, so you can do the same. You can put all your energy of transmitter instead of putting all in one single frequency. You can do the same, but in time. So you can put all your energy in a very amount of time and create some kind of pulse. So that's something that, for instance, optical SETI experiments I was trying to find. So that's basically another way. So there are examples in nature that can create this. So for instance, pulsars, I don't know if you have heard about that, or FRBs, fast radio burst. There are actually some theories that people think that, I don't believe that, but there's very famous scientists that they have papers out there that they can explain FRBs by some artificial means. Okay, there is one more reason why electromagnetic waves is very interesting to send signals, and that's that they are able to traverse our galaxy with not much problem. So our galaxy is full of gas and dust, and that blocks signals. And for instance, optical light is blocked by that. For the case of radio in particular, there is no problem, right? So here in this room, we know that we can get signals from outside. It's kind of the same way. So then what we can say is, like, we don't really need to invoke any unknown physics to when we're talking about finding signals artificially made from somewhere else. I think electromagnetic waves is it's already proven that's since the 60s from these people, Frank Drake and so on. We know that this is the way to go. Okay, so what about which is particularly parts of the electromagnetic spectrum are most interesting? So here in this plot, we have wavelength or frequencies, same thing. We have very large wavelengths. We have radio, and then moving in this direction, we have microwaves, infrared, optical, and even UV and X-rays, right? So what this plot is showing us here is the atmospheric opacity. So basically, if you put an instrument on the surface of our planet, only in some regions you're actually able to see the universe, right? Because the atmosphere blocks all of these regions right here. So that kind of limits, if you're doing any kind of ground-based experiment, to basically optical, infrared, and radio. But there is no specifics on which particular frequency or which particular optical wavelength you want to look. You basically want to look all of that. So that requires a lot of time and a lot of money. So luckily, a few years ago, the Breakthrough LISTEN program started by the Yuri Milner, which is a Silicon Valley billionaire, and decided to help us here. And so this is basically winning the lottery. And we're able now to have access to basically the largest radio telescopes in the world. I'll tell you more about the Green Bank telescope later, but also we're doing some optical observations. So this is really the largest scale SETI program in the history of humanity. So we're very excited about that. And it's already ongoing. We're not really need to wait for 10 or 20 more years to start this. We're already looking for ET. There are many programs within Breakthrough LISTEN, and I just want to give you a perspective on that. Why are we having all these different programs? And for that, I just want to show you this slide right here. How much time do I have? Okay, I'm almost there. So what I'm showing here is the power distribution of transmitters in the universe. So you can imagine that you have power here, a number of transmitters. So you can imagine then that you have some distribution that at low power you have a lot of transmitters, and at high power you don't have that many. But we don't know what distribution really exists. So it might be that you don't really have that many powerful transmitters, or it could be more flat. So for that, we have different projects that we're looking at. So nearby stars, for instance, we're looking at so you're looking for nearby stars. So that means that the power of your transmitter that you're trying to receive is not as strong. You can also look at galaxies, and in this case, we're probing this region here for more powerful transmitters. Kind of going a little bit on time here. But basically, you can also do something in between where you're looking at our own Milky Way and the plane of the Milky Way. So we're basically covering all of these different projects. Kind of just to end, some of the first results that we have from the Breakthrough Listen project was published last year, where we look at 700 stars, 1 gigahertz. And I don't want to go into details now, but I just want to say that sometimes people ask, well, SETI searches have been going on for decades and you haven't found anything. But this is the largest SETI experiment ever done. And you can see it's not that large. I mean, it's only 700 stars and only a small range of frequencies. So there is a lot of parameter space still to look for. And we're very excited that in the next few years, we're really going to increase these numbers quite a lot. There is a lot of stuff that I'm not talking about today. I just want to mention that for those of you that are doing machine learning, we have some collaborations there, or other radio astronomy as well. And if you know any undergrads that want to come to work with us, we actually started our REU program a couple of years ago, and the new students are arriving today, well, yesterday. I just want to finish with this here, which is really very inspirational for me, from Stephen Hawking that passed away this year. I just want to read it to you. To understand the universe, you must know about atoms, about forces that bind them, the contours of space and time, the birth of deaths of stars, the dance of galaxies, the secrets of black holes. But that is not enough. These ideas cannot explain everything. They can explain the lights of stars, but not the lights that shine from planet Earth. To understand these lights, you must know about life, about minds. Thanks.
Thank you very much, Emilio. Do we have any questions?
So all these new surveys and everything with the lottery money are looking really cool, but all of these things that you're talking about, like lasers and radio over any sort of distance, those require both a directional transmitter and a directional receiver. Am I right? Or is that not true for the
not
optical?
necessarily.
Okay. Because it seems like when you have to have a directional transmitter and a directional receiver that are completely uncoordinated, trying to point at the same place at the same time, you wind up having your limiting factor sort of be patience rather than necessarily the ability of your equipment to do something. And does that factor into how these sort of surveys are proceeding?
Right, I cannot to give a general answer. So there is a lot of parameter space to cover, right? So if you get a signal coming from the other side of our galaxy, it takes thousands of years to get here. So this temporality issue, it's there. We also, there is a lot of space and frequencies to cover, and we don't really know what is the preferred option. So what you want to do with any SETI experiment, or what we're trying with our advancing technology, is to increase really this parameter as much as we can. So more time, more frequency, more space in the sky. Yeah.
Well, so I appreciate and I understand about that. The thing I feel challenged about SETI is probably you need to make the instrument like very much cheaper than now. So you somehow can cover basically the whole sky, and for whole many longer time. That is what my thinking. The other thing it's just my thinking. I'm not doing anything with SETI. It's probably that I saw like some people like want to put in like an observatory or telescope somehow to the moon where you don't be limited with the wavelength. So maybe it could be combining with other astronomy projects to do SETI. This just my thinking.
Yeah, I didn't cover much about radio astronomy, but so there is a lot of advancements on what we call wide field radio astronomy. So basically you have these kinds of arrays of telescopes that can cover very wide areas of the sky. So, and this is a technology that is advancing quite rapidly in the last years. There is, for instance, the SKA. This is one of the newest radio telescopes that we're really looking forward to work with. In the case of the moon, Yeah, a lot of us, not just in the SETI community, but also in the astronomy community in general, we're very interested on that. But of course, it's expensive.
So I have a question as well. You put up some figures there that look very optimistic regarding technology, at least at the civilization level that we're at, technology level. 1 to 10 to the 12, really big number. What I'm wondering is, what's your take in terms of the silence? And then the second portion of that, do you have any opinion regarding Tabby Star? Thanks.
Right. Let's see. So I'm not sure if I can really go back. But so basically, the numbers that I was showing is. I'll try to go super quick. So basically, the numbers that I was showing are not. Okay. Well, it's basically the number of stars that you can search, right? So I'm not saying that there are like a million ETs out there. I'm saying that you can search with our own current telescopes. We can search, say, 1 million stars and see if any of those has any signal coming. I'm not really sure about the rest of your question there, but about Tabby Star, I can tell you that there has been a lot of evolution the last year. I don't really have any specifics to say right now, but it seems that I think most of the community is moving now towards a more natural cause than an artificial cause.
Any last questions?
Emilio, so you, I remember from last year actually, you mentioned that you're looking for very, very narrow lines, right? So I know a hydrogen line is pretty sharp and narrow. Can we make anything finer than that?
Sure. So when you have a hydrogen line in space, you actually have it that will be, say, thousands of hertz wide. And many of these masers have the same or even wider. So the signals that we're looking for are, say, 1,000 times narrower than that.
Okay, let's thank Emilio one more time.